Okay, now generally, if let's say you want to see a clear interference pattern, then you must obey further two conditions. Remember just now we had the three conditions for the waves to interfere? In addition to the three conditions, you have two other conditions if you want to see a clear pattern. First one, the sources must be coherent. So why must it be coherent? Now, in an example of, let's say, the two-source interference using like the Young's double-slit experiment, you remember the pattern that we see is alternate bright and dark fringes, right? Now, when you see the bright fringes, it's because at that point, the waves are continuously interfering constructively. So it continuously give you bright. And when the dark fringe is, they continuously interfere destructively, so they continuously give you a dark fringe. So that means they have a constant phase difference at the dark fringe of 180 degrees all the time. At the bright fringe, there's a constant phase difference of 0 degrees. But if you were to have waves that are not coherent, that means they will have different frequencies. So sometimes they will meet constructively, sometimes destructively at every point. So you will never get a fixed pattern. Alright? Now, second condition is the wave amplitude must be equal. Now, why must it be equal? At the position when you get constructive interference, both add up together to get you a bright fringe, for example, right now. But at the dark fringe, you actually get the two waves cancelling out each other perfectly, so there's nothing left over. See, a dark fringe. But if the amplitudes are not equal and they meet destructively, they cannot cancel out each other completely, so you won't get a perfectly dark fringe. So it's hard to differentiate between a bright and a dark fringe. Understand? So these are the two conditions. So now we're going to talk about two-source interference. And when we talk about two-source interference, we're going to see how to set up the apparatus to demonstrate or show the pattern, which is compulsory in the syllabus. So in the two-source interference, I'm going to show you how to set up the apparatus and how to achieve these two conditions. Coherent sources and waves amplitude must be equal. So if you want to generate coherent sources of the same amplitude using water waves, so what we will do is we will need a single oscillator here connected to two dippers. So as the oscillator moves up and down, the two dippers will move up and down, same amplitude and same frequency. So you must use only a single oscillator. If you use two different oscillators, even though they may be same brand, same model, everything same, but there'll be slight differences. So you cannot afford to have any small differences, so therefore you use one single oscillator connected to two dippers. So you need to show them how to demonstrate two-source interference using water waves. So this is a ripple tank, so there's actually some very shallow water inside a transparent glass tank. So what will happen is, as the dippers move up and down, it will hit the water and produce ripples, and the ripples will actually be your two sources of water waves. So when they interact, they will actually meet in the middle here, and then when they interfere each other, you get a pattern. But you cannot see the pattern using your naked eye because water is transparent, so it's hard to see. That's why you need a light source, which is usually a lamp, and then when you shine onto this ripple tank, it will form some shadows here. So let's look at how the shadows look like. So this diagram, don't forget, you got to memorize this. Okay, so what you will see is something like this. You will see some image on the screen. So what you will see is on the constructive interference region, which is here, you will see the water waves traveling. Okay, and then followed by next to it, the water is calm, then water is traveling, water is calm, water is traveling, water is calm. So why does it happen? Because it depends on how they meet. If they meet in phase, then you get constructive. If they meet out of phase, 180 get destructive. So how do we draw? It's like this, very simple. You will notice that from this source A and source B, they drew a solid line to represent the crest of the wave. But the dotted lines represents the trough. So when do you get constructive interference? Is when crest meets crest, that means the crest of this wave meets the crest of this wave, and when the trough of this wave meets the trough of this wave. Example, let's look at this direction. So can you see crest meets crest, trough meets trough, crest meets crest, trough meets trough? Can you see that? But when do you get destructive interference is when the crest of one wave meets the trough of the other wave, or the crest of this wave meets the trough of the other wave. Example, if we take this destructive here, this direction, so you notice the crest meets trough of, this point, crest meets trough, then crest meets trough, you see that? So then you will get a destructive interference. So how will it look like in real life? Okay, so what you will see is this is the two dippers, and then when they will produce the water waves, and where they overlap, you will see waves, and where they to get constructive interference, you see continuous wave. Then you see water is calm one. All right, so let's look at how it looks like. Okay, so you will notice that here the water waves are moving right now, so it's constructive. Here the water is calm, so it's destructive. Moving is constructive. So some people mistakenly think, right, that this is bright, dark, so it's constructive, destructive, constructive, destructive. It's not like that. That is for light, constructive and destructive interference using light. For water waves, this whole thing is constructive. But why you see a bright here is because this is a crest. So it acts, when the light hits the crest, it focuses the light. And the black one is actually the trough. That means it acts like a lens that scatters the light. But because you got crest and trough, that means there are waves here, so this is constructive. But when there's destructive interference, the water is calm, so it neither focuses the light nor disperses the light. So it's just normal brightness, not extra dark, not extra bright. Okay, so don't forget it alternates, and this region whole thing is constructive, destructive, constructive. So imagine if you were swimming across here, you'll notice that, wow, here the wave very big, then here the wave is no more waves and it stopped already. Then here very big waves. Okay, so the next one is to demonstrate two source interference using light. So in this case they call it the Young's double slit experiment, so there's a special name for it. So normally there are actually two ways to generate your light. One is using a lamp, one is using laser. Now if you're using laser, it is easier because we don't need a color filter, but using a lamp you need a color filter. So why we need a color filter is because a lamp, even though the light that we see is like orange color, but it actually consists of many colors add up together. So therefore we use a color filter to produce what we call as monochromatic light. That means light of only a single wavelength. So if we use, let's say, a red filter, that means only red light will come out. So you only get red coming out here. Now this single slit is optional. So if you don't want the single slit, you can just place this lamp and the filter in front of double slit also can. Alright, but you're using laser, they can also skip all this and just put a laser and incident on these two slits as well. Alright, so laser don't even need a filter because a laser automatically produces a monochromatic light. Alright, so when it passes through the two slits, the single source will actually split to two right now. So that's how you produce coherent sources which have the same amplitude. Now some people say if I use two similar lamps, same brand, same manufacturer, put in two lamps here, one here, wouldn't it be the same? I say that even though it looks the same color, got the same manufacturer and all that, but the waves coming out from a lamp is never continuous wave. So you don't expect the wave coming out from a lamp to be continuous. There's always breakage. That means sometimes it will have for no reason no wave for a while, then it continues. Why? Because the how light is produced from a filament lamp is the electrons in the filament gains energy after the filament is heated up, and when they jump to a higher level they become very excited, higher energy level. So when they fall back to a lower energy level, they will lose the energy as light. But this falling and going up are all random, so you can never continuously produce a light wave but you cannot notice it because it's only for a very short time only. But if you're talking about producing coherent sources, then you can't. But if you have the single lamp split to two, then no problem. If there's a breakage here, there's also a breakage here, so they'll always be coherent, right? And same amplitude So what will we observe here? Now you notice that the wave here spreads from this source and the wave here spreads from this source, right? So where it overlaps is only here. So you only see a pattern here, not here, not here. Right now, so this pattern here, you will see alternate bright and dark fringes. Now when you see bright and dark fringes, some people have the idea of seeing white and black, which is wrong. If you're using, for example, red light, right, the color that you're going to get for constructive interference is red. And then destructive interference, nothing, no light. It's not black, it's not no light. They call it dark fringe, not necessarily black fringe, you see. So if you're using blue light, then constructive interference part you get blue. Destructive you get no light, not black. Understand? Okay. So make sure you know how to draw all these apparatus, but you don't have to draw this, what do you call it, this if you want to use a laser lah, and then you can get rid of single slit if you are using either laser or lamp. Okay, the one you can optional. So this is what you will see lah. If you place the light source, alright, which is a lamp here, you put a color filter, then it enters your two slits, then you will see, can you see alternating bright and dark fringes? But you don't get black, you just get dark and bright. Understand? Okay, because this one is blocking the light, so it's nothing like just shadow on you, but it's not necessarily black. Okay? So the next example is how to demonstrate two source interference using microwaves. So if you are using microwaves, then you need two metal slits. Yeah. Alright, so why you use metal slits is because microwaves cannot pass through metal. So then it will split, then you will get the pattern. But the problem is if you're using microwave or ultraviolet or infrared, you cannot see any of them because they're invisible. And it's not like sound. If you're using sound, then you can hear. So you cannot see, you cannot hear. So how do we know where it's constructive and destructive? You just use a detector. So when you draw, you just put a detector. If it's microwave, you call it microwave detector. Ultraviolet, you call it ultraviolet detector. And infrared, you say infrared detector. That's all. Okay? Now, for sound, how to draw? So if you want to generate for sound waves, two source interference, then you need a signal generator, which we can call audio frequency generator, a specific type of signal generator connected to two speakers. Alright, so when you connect the two speakers, because it comes from the same source, so no problem about being coherent. So then we move a microphone. So let's say we have a microphone here connected to what? You must connect to a CRO. Okay, maybe I write the CRO on top. Sorry. Because the CRO will show you the amplitude. So if you move it from here to here along this line, you will detect high reading, low reading, high reading, low reading. So that indicates constructive or destructive interference. So this is what you just draw. Okay? So if you want to see how it looks like, right? So maybe you can write the CRO on top here. Okay, so the screen, what should we see? Now if you turn on the time base also can, you turn off the time base also can. If you turn on the time base, it's a bit hard to see the amplitude because what you will see is a waveform. Okay, but you can still know where it's constructive or destructive, because constructive you will see a continuous wave like this, destructive you will see like that. But if you turn off the time base, it's a bit easier to see because once we turn off the time base, if it is constructive, then you will just see as a straight line. Destructive, you see a dot. Okay, so either way is fine.